Okay, so we are continuing today with the extended response questions for differential equations. You'll see a lot of similarities to some of the ones we've done before and some of the stuff that we did on individual lesson days. Again, just trying to expose you to as many of the different versions that we've seen on the AP exam that we can. Okay, first question says make a slope field for the 9 points indicated using our differential equation dy dx equals 1/2 x plus y minus 1. Okay, so my suggestion, as I had mentioned in the previous video, would be to make some sort of a table of values. You can see that your x's, again, which go horizontally, you're going from -1 to 1, okay? And then obviously you want to separate those into columns. Then we're going to put our y's down the left-hand side. The y values we use in this problem are 0, 1, and 2. So therefore, I'm going to put 0, 1, 2. So therefore, when I actually do my calculations for each of these boxes, they correspond with those 9 points that are actually in the slope field. So as I had mentioned before, my suggestion would be to make sure that you start with like keeping your x the same or keep your y the same or something like that, so your values don't change too much. So maybe I'll start with even like 0, because I think that might be the easiest one. Let's start with x being 0. If x was 0, then I would only have to care about what y minus 1 is, because the 0 part would just be 0, so it wouldn't change anything. So if I did y minus 1, that would be 2 minus 1 would be 1. Let me do it in a different color. Good. Okay, so 2 minus 1 would be 1. 1 minus 1 would be 0. 0 minus 1 would be -1. Okay? And I do want to kind of point out, see how this pattern is, that I go from 1 to 0 to -1 down in that middle column. I'm decreasing by 1 whole unit. Chances are that's probably going to end up being some sort of pattern that I'm going to end up using when I get to my next, rows or whatever, columns. So let's start with x equals 1. So that would be 1/2 plus 2 minus 1, which comes out to be 3/2. And then I do the next one. 1/2 times 1. Okay, so 1/2, I'm sorry, the last one had been, sorry. So this would be 1/2 times 1 plus 1 minus 1, which comes out to be just 1/2. And then finally, eventually, this comes out to be -1/2. And you can see, once again, you're subtracting by 1 as you go from term to term. So once you figure out this one, all you'll really have to do is then go and keep that pattern of subtracting by 1 to be able to get to the next one. Again, these are just ways to check yourself if you don't want to calculate each value individually. Eventually, you'll find out this comes out to be 1/2, -1/2, -3/2. Okay, so when you put these on your graph, again, you don't really have to make those exact slopes. The only one that should really be exact is the one at 0. All the rest should basically show a transition, getting more steep, getting less steep. So maybe I'll start with like this first row right here, going from 1/2 to 1 to 3/2. So 1/2, kind of a positive slope, but not that steep. 1, positive slope, more steep. 3/2, positive slope, even more steep. Okay, and then obviously I'm going to do the same thing as I go through the next ones. So notice how this first one in the top left-hand corner had been 1/2, and I see the one in the middle row on the right-hand side is also 1/2, so I'll try to match that. That's the best you can do again. And then if I look on the other side, I want basically the same slope I just drew, but now in the negative direction. That also matches the one on the bottom right-hand corner, so I'm going to try to match this same one, and then you can see this becomes -1, a little more steep negative, a little more steep negative. Okay, so there's my slope field, so I have an idea of what my solution would look like, especially because this is a non-separable differential equation, so I won't be able to solve this the way that we were solving the previous ones. That means this question is more about analysis that I'm done after, as opposed to working backwards to the actual original particular solution. Okay, so I'm going to get rid of this now, so I have a little bit more space. And let's go on to the next one. So it says find the second derivative in terms of x and y. So remember that essentially when you're doing differential equation second derivatives, you are doing implicit differentiation. As you take the derivative of a variable, everything we're doing here is in terms of x. You have to follow it up with d of that variable over dx. Okay, so that way you don't forget stuff. And remember, when you do second derivatives with implicit, there's always a point where you're going to have to plug back in the original derivative. So my second derivative will start looking like this. The derivative of 1/2 x is 1/2 dx dx. Okay, the derivative of y is 1 dy dx. And then that -1 comes out to be 0. Dx dx goes away, so I end up with just 1/2. Dy dx, what I'm going to be doing is I'm going to be plugging back in my original dy dx in that place. So this is going to be plus 1/2 x plus y minus 1. I guess technically you could leave it like that because it doesn't really have to be simplified. But if I did want to simplify it, it comes out to be 1/2 plus y. Yeah, 1/2 x, I'm sorry. 1/2 x. Let me erase that because I don't like the way that looks. Okay, so 1/2 x plus y minus 1/2. So you're not just asked to solve for that second derivative, you're actually asked to use that to figure out when your curve is going to be concave up. In order to have a concave up curve, you need a second derivative that is greater than 0. So pretty much all you have to do to answer this question is say, I have 1/2 x plus y minus 1/2 is greater than 0. That's what yields something being concave up. If you wanted to get this more in like an equation type form, like similar to y equals mx plus b, you could get y by itself. So then eventually that would come out to be something like y is greater than negative 1/2 x plus 1/2. So what this means is that, and if you remember back in the day when you did linear inequalities, if I were to graph this function, negative 1/2 plus 1/2, it looks something like this. All of my values that end up being above this dotted line will end up being concave up. That's what I'm getting from this information. Again, you don't really have to. I'm pretty sure that if you left this answer right here, that would be just fine. Okay, so going on to the next one. So I want you to be careful with the next one because sometimes people see particular solution and they jump right into doing the stuff that we were doing before. But as I just mentioned, this is not a differential equation that you're going to be able to solve. This is one that you're going to have to be able to do something else, like the slope field or something else. This question is not asking you to solve. This is asking you to find out, do you have a relative minimum or relative maximum or neither at x equals 0? So I want you to think back to curve analysis stuff. When you wanted a relative max or a relative min, generally what we had done is we would have done a number line, we would have looked at a critical point, how do the signs change, is it going from, increasing to decreasing, but there's a problem here. I only know one point on this curve. So I can't, unfortunately, do a number line analysis. Okay, I would need more points to be able to plug a full XY pair into this differential equation. So the first thing you are going to check, though, is you are going to check for a critical point. Does the point 0, 1 that they give you a derivative that equals 0? Because that's what needs to happen if you're going to have a turning point. Okay, so if I plug in my dy dx equals 1/2 times 0 plus 1 minus 1, and as I simplify that, that does come out to be 0. So it means there's a possible relative minimum or relative maximum. Here's how you get the second part of this. So it turns out that after you do that first derivative and find out the derivative is 0, and I will tell you, if that wasn't 0, you're actually done at that point. That would be the case that came out to be neither. Because the fact this comes out to be 0, I know it's either going to be a relative min or relative max. If you notice what's happening, when it's a relative minimum, that means I'm concave up. If it's a relative maximum, I'm concave down. So what I'm going to do is calculate the second derivative using the same point they gave me. So my second derivative, again, if you remember, was 1/2, what was that, x plus y minus 1/2. So if I plug in 1/2 times 0, plus y, which is 1 minus 1/2, comes out to be a positive 1/2. Okay, so therefore, or actually you just really have to care about the fact that it comes out to be positive. So it comes out to be positive 1/2, which is greater than 0. So you would say, since the curve is concave up and dy dx equals 0, there is a relative, okay, so let's think about this for a second, concave up and a turning point. You could see right here that's a low point on the curve. There is a relative minimum. Okay, so if you see any questions like that ask you for relative min, relative max, or neither, again, first thing you do is you have to check that the derivative comes out to be 0. If the derivative wasn't 0, there's no possible way that it's a turning point, and then you're just finished and you say neither. If the derivative comes out to be 0, you check the second derivative, see if that comes out to be positive or negative, so therefore the fact that it's positive, concave up, and a derivative that's 0 is what yields a relative minimum. Okay, so the last one probably looks trickier than it actually ends up being. But it, because you have to basically think of this question as a system of equations. So it's saying find the values of the constants m and b for which y equals mx plus b. What kind of a function is that? That's a linear function. So let's think about linear functions for a second, okay? So they're giving us one of our equations for our system, y equals mx plus b. A lot of unknowns there. I have to solve for m and b, and I'll probably need an x and y at some point. So let me think about what I know because it's linear. Well, if you remember, if you have a linear function, that means that you have a constant slope. That slope is m, and that slope is another way of saying the derivative. So that basically tells you that the derivative is equal to m. So my dy dx is what they gave us in that problem. We know the dy dx is equal to 1/2 x plus y minus 1. Okay, so now I have a second equation. Again, still a lot of unknowns in this problem, so I have to do a little bit more. We'll think about a linear function for a second. What kind of concavity does it have? Is it curving up? Is it curving down? It's not curving at all. That means that I have a second derivative that's equal to 0. Okay, and if you remember, we had found the second derivative before, so what I'm going to do is I'm going to erase this quick and put in the second derivative that had been 1/2 x plus y, what was that, minus 1/2, okay, and set that equal to 0. And then from here, now I have 3 equations I could use to solve for the m and the b. I would suggest starting with this last one, the one all the way on the right-hand side, because of the fact that that's only in terms of x and y, and I don't have any additional things to work for. So like basically, I'll use that first equation, and when I move everything away from y, I end up getting negative 1/2 x plus 1/2. Okay, so once I get that, that's negative 1/2 x plus 1/2. Now I can take this equation, and I can substitute it in place of y in that second expression. Okay, so let me start filling that in. M equals 1/2 x. Instead of y, I'm going to plug in this whole expression, negative 1/2 x plus 1/2 minus 1. So I end up starting to, clean this up a little bit. 1/2 x minus 1/2 x would be gone, so that actually cancels out. And now I have 1/2 minus 1, which comes out to be negative 1/2. So now I at least know my m value. Okay, so I'm going to go back over to my first equation, and now I'm going to rewrite this as negative 1/2 x plus b. Now, if you remember from that third equation, we knew y is also equivalent to negative 1/2 x plus 1/2. So I can once again substitute that in for y. So I have negative 1/2 x plus 1/2 equals negative 1/2 x plus b. You'll see those negative 1/2 x's cancel out, and I'm left with b equals